To calculate the delta H, or change in enthalpy for a reaction or process, we use this equation. We add up all of the H formations of the products, and then separately do the same for the reactants, and then we subtract the reactants from the products. So this little epsilon sign means the sum of. So we take the sum of all the H's for all the products minus that of the reactants. To do the delta S of a reaction or process, we do the analogous thing just with the S values, okay? Now, looking at our Appendix C in our textbook for students who are taking this class from me, you can extract from that the individual delta H of formation values under standard conditions. They have units of kilojoules per mole, by the way, and insert them where they belong for each term. You can do the analogous thing for the entropy values, which are in units of joules per mole Kelvin, or as I like to call it, joules per molk. And you can insert them in here. One thing that I pointed out elsewhere, by the way, is that if you have a substance in its elemental formula and physical state, solid, liquid, or gas under standard conditions, its enthalpy of formation is equal to 0. So depending on which table you're looking at, and for any of you who don't have access to the table or textbook that I'm talking about, you can probably just look on the internet, enthalpy table or thermodynamic table or entropy table or something like that, and find these same terms. Anyway, what I'm saying is here we've got hydrogen. Does hydrogen in its elemental state have a formula of H2? Yes, it does, because it's a diatomic element. At 298 Kelvin, which is roughly room temperature, 25 degrees Celsius, is H2 a gas? The answer is yes. So its delta H of formation is 0. Analogous questions for F2, totally correct. So its delta H of formation is also 0. So if you look at a table and you don't see values written for these, the reason is because it's understood, or should be understood, that these substances don't need to have it written into the table, because you know that that's their formula and that's their physical state, solid, liquid, or gas at 298, or roughly room temperature 25 C. Does that make sense? Now, all of that stuff about these being 0 for delta H of formations is not true for S values. S values, that is entropy values, are never below 0. They can only get down to 0 if you go all the way down to super cold at 0 kelvins, or negative 273.15 degrees Celsius, which is absolute 0. And you'll never get a negative value for any of those, okay? And understood, we're talking about standard state conditions, which is 25 degrees Celsius or 298 kelvins, so we'll never see any zeros across the board. Okay, so with all of that said, now we have our terms. Let's insert them into their respective locations in order to get our answers, okay? So for delta H for a reaction, we're going to take our products here. We've got negative 268.61, but you'll notice that there's a coefficient next to that of 2. So we have to multiply this by 2, okay? So that is going to be the sum of all the delta H's for our products. In this case, there's only one product. And then we're going to subtract from that the sum of the delta H formations of our reactants, which is going to be 0 plus 0, okay? So I'm going to throw all that into my calculator, and I end up getting negative 537.2, and of course the units are kJs per mole, okay? So that's my delta H. How do I do it for delta S? Well, I do the analogous thing. I guess what I can do is I'll just erase all of these H's and replace them with S's, but I'm using the otherwise same equation, right? I'm going to take my S value for my product, which is 173.51, and I have to multiply it by 2. And then I'm going to subtract from that the sum of all of my S values for my reactants, okay? Now there's an implied 1 coefficient, not written but understood, next to each of these reactants, so I don't need to multiply these things by anything except for 1. So I'm just going to take here the sum of 202.7 and 130.5. Plug this into your calculator. You should end up getting positive 13.74 joules per mole Kelvin. So here's my answer for delta H. Here's my answer for delta S. And that all lines up beautifully with answer B.